Hi, I'm Ben.
Hello, I'm Ani.
I am Derek.
I'm James.
And I'm Julie. On behalf of Team 13403, I would like to thank the judges for naming us finalists this year, and let's charge right in. This report is intended to convey our approach to the three parts of this year's Keep On Trucking M3 Challenge. So let's start with a brief outline of our presentation. In problem 1, Shape Up or Ship Out, we determined the population of semi-trucks, both diesel and electric, in the near future. In problem 2, In It for the Long Haul, we created an algorithm to optimize charging efficiency for trucks along major highway corridors. And in part 3, I Like to Move It, we devised a metric to prioritize corridor development by estimating the monetary value of community, social, economic, and environmental concerns.
Hi, my name is Ben, and I'll be presenting the first part of problem 1, Shape Up or Ship Out. To give a quick restatement of the problem, the goal was to model future semi-truck demographics, assuming that all essential electric truck infrastructure exists. We made a few key assumptions for this problem. Firstly, that all trucks are either diesel or electric. This was due to a lack of data for hybrid trucks, as well as to preserve the simplicity of the model. Next, we assumed the average lifespan of a truck is 12 years. Finally, we assumed that all new trucks would be electrics and be replaced after 12 years, since electric trucks are more cost efficient than their diesel counterparts. To model the total number of electric trucks, we developed two variables, CT, the total truck population, and DT, the total diesel truck population, where T represents years after 2019. This is true because assumption 1 states that trucks are either electric or diesel. We determined C of T to represent total demand for trucks, and it naturally grows with population and follows business cycles, which is relatively linear. The model was based on historic growth, and our equation is shown with R-squared value. DT, the diesel truck population, was modeled using current age distributions by shifting the current distribution forward into future years. In order to further develop our model, we solved the inequality involving respective operational and manufacturing costs for both diesel and electric trucks for T star, the age at which a relatively new diesel truck should be replaced with an electric truck. Solving the inequality, we found that a diesel truck younger than 3.6 years should be replaced with an electric truck. From assumption 3, we also know that a truck older than 12 years will be replaced with an electric truck. Now, Ani will talk about curve fitting for modeling age distributions.
In order for us to now model truck age distribution to compute DFT, we chose to use an advanced curve fitting scheme. Specifically, we employ the Gamma-Gompertz distribution to approximate the age distribution of trucks. There are a couple of key reasons we believe this model would be particularly effective in this scenario. Firstly, the Gamma-Gompertz model is traditionally used as a model for consumer lifetime, and the lifespan of trucks is somewhat analogous to this. Also, the boundary conditions on this distribution match the expected trends for truck age distribution. Specifically, there's a non-zero probability density for t equals 0, and the probability density decays to 0 as t approaches a large number, which makes sense. Now, in order to actually fit the distribution, we use the probability density of the Gamma-Gompertz function, shown here, and SciPy's curve fitting functionality in order to determine the parameters b, s, and beta, which are all greater than 0. Now that we've done this, the simple task of iterating the present age distribution to determine future age distributions remains. We take the present age distribution of diesel trucks and shift all points right by 1 year to determine the next year's distribution. Then, we remove those points less than t star and greater than 12. We do this until no points remain or 10 years are reached. Notice from the graph that by the end of year 8, no diesel trucks remain. This leads us to our final results. Our final results predict that 60% of trucks are electric by 2025, and all 100% of trucks are electric in 2030 and 2040. These numbers are within 25% of a market research study by P&S, truly electric.
Hi, I'm Derek, and I'll be presenting the first part of problem 2, which says, create a model that optimizes the number of electric charging stations and chargers per station along highways to sustain the current freight for 5 different highway corridors given to us in the problem. So in this problem, we had many assumptions, but here we'll summarize the most important ones. The first was that each station has 9 chargers, so that solves one part of the problem. And we got 9 chargers because that is the ratio of Tesla's existing superchargers to the number of existing Tesla stations, which you can find on the internet, and you get 8.86, which is close to 9. Also, it's difficult to vary the number of chargers per station for each highway exit without knowing more information about the highway exit. So we try to keep things constant. We also use level 3 station chargers because they are the most efficient. And every corridor is going to start with a charger because we have no information about the route prior to the corridor interval. So our algorithm will start with a charging station at the first point. And we also assume that the distance traveled from any charge percent is constant, so that the charge percent is linearly proportional to the distance trucks can travel. So now we need to calculate the total number of chargers. And to get that, we are going to use the formula C equals T divided by 14,400, where T is the distance traveled by all trucks in a day. And how we got the 14,400 value? Well, each charger takes at max 30 minutes to fill a truck. So in a 24-hour day, each charger will get used at max 48 times. And another assumption we had was that each truck goes 300 miles before needing to go to a station. So the number of chargers is T divided by 48 times 300. So we just need to find T. And T is the sum of the interval lengths multiplied by the sum of the lengths of the intervals multiplied by the number of trucks per interval. And the interval length is the distance between consecutive markers. And we used an integral where we set f of x to be the AADTT values given in a question, and we integrated using the midpoint Riemann sum. So we summed the interval lengths multiplied by f of the midpoint of the x values for each interval. And because we are assuming linearity, this midpoint Riemann sum turns into a trapezoidal sum. So we can replace f of xi plus xi minus 1 divided by 2 as f of x plus f of x of I minus 1 divided by 2. So we can calculate t while using only the AADTT values. So what's the answer to this problem? Well, we need to find S, and we assume that there are 9 chargers per station. So we need at least ceiling of C divided by 9 stations, and we're going to place a station every T divided by S miles, where T is the total distance traveled by the trucks in a day, and S is the number of stations, with 1 station at the start of the corridor. And to find out precisely where are the charging station positions, we can use the 4th equation to do that. Now, let's see some of our results. And as you can see, the busier the highway corridor, such as the San Antonio to New Orleans highway corridor, we need more stations, and the other 4 highway corridors also make sense as well. So now Ani will talk about the algorithmic implementation for this problem.
This flowchart depicts the algorithm that we've described thus far. I'm going to briefly walk us through the Python implementation of this program. We start by loading the truck traffic data as a CSV using the pandas module. As mentioned, we interpolate linearly between data points using NumPy's interpolation method. Then, we determine C and T and initialize a set of stations to the start of the corridor. We perform an integral until we reach the cutoff point using a trapezoidal integration scheme. Once the cutoff has been reached, we simply append the relevant position to the list M. We keep iterating this until the max distance is reached. Let's take a closer look at the result of this algorithm on the Minneapolis-Chicago corridor. In fact, this graph perfectly summarizes our work for the second problem. The y-axis represents truck traffic, and we do notice that higher traffic results in more closely spaced stations, as seen here, and lower traffic results in further apart spaced stations. Additionally, the total number of chargers meets the requirement. Not shocking at all. Let's move on to problem 3. I'd like to move it.
Thank you, Ani. Now I will talk about the third problem. In this problem, we ranked national corridors for transition to electric trucks based on community, economic, environmental, and social motivations. Let us cover a few assumptions. Firstly, corridors with higher monetary benefit per capita should be targeted for development first, For non-financial factors, a reasonable monetary cost can be determined that results from the factor. By unifying every factor into a common unit, we make them easy to compare. Money is also less subjective than other ranking units. Next, we assume that infrastructure will be built and all trucks will be electric within 8 years. This is based on our result from problem 1. Finally, we will disregard possible changes to electric trucking technology, as such changes will affect all trucks equally, so they do not change our relative rankings. With these assumptions, we can use current trucking numbers to represent the number of electric trucks on the road in the future. Our overall metric, T, the total monetary benefit per capita, is the sum of 4 factors, O, E, I, and U, divided by P, the number of people living near the corridor. O was found by finding the difference between operating and manufacturing costs of electric and diesel trucks, then multiplying that number by AADTT. Next, since electric trucks do not produce emissions like diesel trucks, we considered E, the monetary benefit of avoided emissions. E is the total volume of emissions produced by diesel trucks, multiplied by the cost of a ton of emissions that we found in a Stanford study. I is equal to the installation and lifetime usage costs of electric chargers multiplied by the chargers needed in each corridor, which we found in problem 2. U is the communal profit from the usage of the new electric truck infrastructure, which we assumed would benefit local residents near the corridor the most. It is found by multiplying together the average number of charges per truck in the corridor, the profit per charge, the number of trucks per day, and the days in the lifetime of a truck. P, as described before, is the people living near the corridor, which was taken directly from census data of people living near interstate highways. Pulling our data from a variety of sources, we were able to find monetary benefit per capita for each corridor, which is summarized in the rightmost column. Our final rankings are shown here, with the Jacksonville-Washington, D.C. corridor ranking first and the Boston-Harrisburg corridor ranking last. They make sense as corridors that receive more truck traffic generally should have higher benefit and should therefore be targeted first. Now I will pass it on to Julie, who will talk about conclusions and future work.
So our treatment of these 3 problems make it very clear that even at current infrastructure and technological levels, the semi-truck industry is ready for electrification. More precisely, we determined that 1, within 10 years, as used trucks are spent and companies seek to lower long-term costs, fleets will transition to fully electric. 2, we created a second model to spread out the most efficient necessary infrastructure along major corridors. And 3, we evaluated social costs along major corridors to conclude that the Jacksonville-Washington, D.C. corridor should be prioritized for electric infrastructure development. When it comes down to the details of implementation, with more time, we would love to expand on our current models. For Model 1, looking at our graph, the function seems to oscillate, perhaps due to seasonal business demands. So for more accuracy, we could use a quasi-periodic function instead of a straight line to model the truck population. For Model 2, a more practical general model would consider existing infrastructures such as truck stops and surrounding services. So a better model would layer new infrastructure on top of what already exists. This would, of course, require more AADTT data and business data. For Model 3, our model used constant current truck numbers and generalized cost categories. For further studies, we could model the growth of trucking for each corridor and add parameters within our equation. For example, we could look at the politics of support behind novel infrastructure decisions in certain regions and incomplete combustion from differential burning sources in electric generation. So in light of current shocking circumstances, unfortunately, we can't answer any questions live, but still we would be ecstatic to answer any questions you have virtually. Additionally, we believe that these repositories have a lot of potential to spark inspiration for future teams from our school and across the country. Thank you again for your time and consideration.